Okay, so in the previous video we talked about pKa, what it means for the strength of the acid. Now we're going to take a look at a couple of things that can affect the pKa of a given functional group or a given molecule. First thing we're going to take a look at is electronegativity. So the electronegativity, the more electronegative X is, the more polar this bond is. So we're going to assign a delta negative to X and a delta positive to H. Okay, and what's going to happen is as you increase the electronegativity, the general trend is you lower the pKa. That's because you make this bond more polar. Okay, and the polarity of this bond and how polar it is really has an effect on how easily the H can pop off. The more polar your bond is, the easier it is for the H to pop off, because the more polar your bond is, the more electronegative X is going to be, and the more electronegative X is, the more it likes electrons, the more it's likely to just steal these two shared electrons and have the H leave and go off into solution. Okay, so with electronegativity, one of the general trends that I've always remembered is Dr. Funkelbrisk, PhD. These are your most common atoms that you're going to see in a given organic molecule. So what's cool is if you group everything, like, fluorine's your most electronegative element. But F, O, and N, it starts off with the second row elements, and then it talks about your halogens with the Cl, Br, and I, and then you have sulfur, carbon, phosphorus, hydrogen. Okay, so Funkelbrisk, PhD, just a handy way to remember your most common electronegative elements. All right. Now, one thing that you do need to keep in mind about this electronegativity trend is it only really works when you're staying in the same row of your periodic table. Okay, this trend isn't very good if you go between different groups, okay, or different rows of the periodic table. All right, so let's say you go down a group. Best example I can think about is methanol versus if you change the O for an S, and also the halogen series. So let's take a look at the pKa value of methanol. This one is going to be roughly about 15 for the pKa, whereas if you replace it with a sulfur, pKa drops to 11. So that is completely opposite of what we said with electronegativity. Sulfur being less electronegative, according to Funkelbrisk, PhD, should have a greater acidity, and sulfur being less electronegative should have a worse acidity and a higher pKa. Whereas methanol, the oxygen, is more electronegative, it should have a greater acidity. And the thing that you have to keep in mind is, more important than electronegativity is the radius, okay? The radius of the atom, because what the radius does is it helps stabilize your conjugate base, and when you stabilize the conjugate base, it makes it weaker. Weaker conjugate base, aka more stable, means more acidic compound, lower pKa. And where this becomes really, really apparent is with the halogen series. So HF, even though it's really electronegative, is considered a weak acid. There's going to be some equilibrium going on inside solution. Whereas HCl, HBr, and HI, these three are strong acids. You're going to have like 100% dissociation. And what you really need to look at is actually the radius size of the conjugate bases. Like if you look at fluorine, it's a really, really small atom, okay? And you're trying to spread this negative charge over a really small area. It's not going to be all that stable. Compare this to chlorine, which is going to be much bigger. Spread the negative charge over a larger area, stabilize the molecule. Br gets even bigger, and I is really gigantic, okay? I didn't really draw that to scale very well, but it's big. Okay, so radius, what that does is the bigger the radius is, I've always thought of it as it helps stabilize the resulting negative charge on the anion. Okay, now in summary, one thing you can use to remember the whole periodic trends on the periodic table is Baer. You start with the top left corner, B-E-A-R, and you go clockwise. B stands for basicity. E, there are three trends that involve E: electronegativity, electron affinity, and energy of ionization. A is acidity. Notice that it's lower than the electronegativity chart, which agrees with the whole thing that we said radius is more important in stabilizing the conjugate base than electronegativity. With electronegativity, you just need to get to the right side of the periodic table to form an acid rather than a base. But then among elements of similar electronegativity, the radius becomes more important. And then finishing up in the bottom left corner, you have your maximum radius. Okay, so if you ever need to remember your periodic trends, starting from the top left corner, BEAR, that gives you your maximum values.